you know is Beatrice Fu. He's currently my colleague at Cadence. Is a great technologist that actually crossed the two domains that we mentioned today. The PC era, he was a designer for the i486, you're familiar, and a decade ago he moved to the other side. He was doing the SoC, and he was a co-founder of Tensilica, which recently become part of Cadence IP family. And she's currently a VP of R&D at Cadence IP Group. Today, she's going to deliver a bit more technical on the SoC level and look at it, say what are the challenges that the designers facing in putting an SoC together, and where does the solution come from? So let's welcome Beatrice Fu.
Okay, first of all, I have to apologize for Pankaj, who is my colleague in Cadence. He's scheduled to be here, but he cannot make it today, so we have to make a last-minute substitution. I hope I will be an adequate substitution, and I'm new to Cadence, but I have been in the, as Brandon has mentioned, I've been in-house in the first part of my career in the PC industry, and spent the last 15 years actually founded and started an IP company, Tensilica, and we just recently got acquired by Cadence. That's why I'm here today, representing the Cadence IP division. So you may not think about it that way, but we are all in the semiconductor industry. Semiconductor has actually added a revolution to the human history, just like the Renaissance and the industrial revolution. In Renaissance, it has enabled individuals to be more productive, to accomplish more things by mechanization, like wheels and mechanical. And in industrial revolution, it has enabled a small group or a local group of people to work together on physical products, like electrical-based or steam-based machines. And the semiconductor revolution has enabled a global collaboration of a variety of projects, hardware, software, science, entertainment. And it has greatly improved the humanity and society in the last 50 years, just like actually as much as the Renaissance and the Industrial Revolution in hundreds of years. And this semiconductor revolution, for those of you maybe old enough as me, probably this is older than me too, started from the first transistor-based computer. Before semiconductor, if you go to the Tech Museum, the Computer Museum, you see the old vacuum tube computer. Those vacuum tube computers are huge, by the size of this room. They're expensive, they're slow, and they're actually unreliable. Semiconductor is actually what makes computing practical for the business application. Before that, all the computing is just for scientific laboratory or experiment. So when the first wave of transistor-based computers were introduced, it was in the early 60s. History. In those days, people thought that, oh, this world probably needs a few computers, maybe 10, 20, at most 100. By 1970, there are 1 million mainframe computers. Now, 1 million doesn't sound a lot today, especially if you listen to John's talk about things are talking about billions of that. But in those days, in 10 years, for new technology to have that kind of growth is an explosive growth. And that growth did not stop. The semiconductor revolution continues. Right? Those of you who work in the industry, is IC, integrated circuit, and Moore's law, which is about transistor scaling. that enabled microprocessor and the birth of the personal computer in early 80s. So the whole PC industry come from there. And in a short time, that was, remember, the first PC, like I think the IBM PC is 1981 and Apple's about that time too. By 1990, there are a billion PCs. The PC industry has grown to a billion in the 90s. And we are all in the middle of it. Now, you all know, like the PC, especially the latest news, the PC shipment has declined. A billion is still a big number. In fact, I believe that in year 2013, the shipment for PC units is still going to be like more than 300 million units. So the peak is close to 500 million a year. So I think some of you are from Intel here, you can already confirm those numbers. So it is a big growth. And ironically, the reason for the decline is because of this semiconductor revolution has driven a different kind of, continue to drive growth, but on a completely different platform with even higher volume. So today, there are 10 billion connected devices. I know John mentioned it's about 5 billion mobile phones. Now, this is the number of different of our marketing and ARM's marketing, but I believe this number also does not just like PC and tablets, also like medical devices, home appliances, and these like the notebook. So it's just a lot of devices there. I mean, the population is only 5 billion, and this has more devices out there than the population. And we believe that, as the earlier talk has also alluded to, this growth, this volume growth, this semiconductor revolution is continuing, and it's driven by these big trends here. And some of them you see it day to day, like mobile devices. I'm sure everyone here carry at least one, if not more, handheld devices. And video cameras is everywhere. The social networking is driving a huge volume of network traffic. Some of the other trends like cloud computing and the Internet of Things, and also the big data are kind of behind the scenes, but they are growing rapidly too. Just like John mentioned, the Internet of Things is growing at 23% a year. So, and in fact, all these behind the scenes growth are also fueled by the amount of communication and the rich data that we're seeing in our day-to-day. So the underlying enabler of this big trend is the advance in semiconductors, because the semiconductors are the heart of everything electronic. So in fact, that should be great news. It's really great news for the semiconductor industry, especially for the chip maker, because like all this big trend will drive new applications, higher demand on the product. So that means we have to design new products and new chips. So that was definitely great news. In fact, it was projected. Now, this data, I believe, it comes from Morgan Stanley, which is also different from John, who said it's only 30 billion. But our marketing say that it's 50 billion mobile internet devices by year 2020. It's close enough. We are talking about 7 years away. So 50 billion. And that is, the trend also do not just start at the mobile internet, but also in the automobile industry, industrial, home entertainment. So the growth is going to be there. It's going to be phenomenal. So, which is all good news. On one hand, we have this tremendous growth. It's going to be like fields of semiconductor industry could move forward with lots of demand, lots of new design. But on the other hand, if you notice, and those of you who are, if you are in the design area, you know that designing this semiconductor chip is actually getting more and more challenging. System on a chip has been the heart of all these complex semiconductor devices. System on a chip means that there is a processor and there's other logic. It's almost like a system that you integrated on a chip and has been the term since, I would say, mid-90s. So the system on the chip is basically the underlying basis for these complex semiconductor devices that deliver the complex functionality and also give you the rich experience. That's where it comes from. And the SoCs are everywhere. In fact, earlier I was a little surprised that when I saw John's data that the penetration of the mobile phone outside in some countries, or at least for the smartphone, wasn't that pervasive. And I have to relate my own experience. I just come back from Bhutan 2 months ago. Bhutan is a country which doesn't have internet until year 2000. And in fact, I don't think it has currency until 1960 something. But when I go there, go to the airport, to the hotel, go to the shop, they all have a smartphone. So I was thinking, this trend is actually going very pervasive. It's getting there. They are getting it. So, but the challenge, building the SoC is getting to be more and more challenging. First of all, one of the things is Moore's law continue to hold true. The number of transistors on the chip doubles every 18 months or 24 months, depends on who you talk to, but it continues to increase. That means the transistor budget continues to be there. You can integrate more and more complex functions on a single chip. But the problem is if you have to design every single one of those complex functions from scratch, it is a daunting task. So many people turn to IP, and that's where we come from, for more IP blocks, such that to mitigate the schedule and the time to market risk. But if you take the off-the-shelf IP blocks, a lot of the times they're the black box. Making those to work with your other logic, or even with some other IP blocks, has its own set of challenges, sometimes could be detrimental. And we can go to more of that. And also the Moore's law is about transistor scaling. The geometry is getting smaller and smaller, and then we are building more and more complex devices. To design to that advanced node take a lot more effort and care these days, even with the help of the EDA tools, including cadence tools. And with those complex circuitry, packaging, and power, all those are big concerns. I mean, I don't know whether you see, if you go to, sometimes you go to these graphics, high-end graphics game machines, and you see the packaging of all those graphics chips, you see the heat dissipation and the density, the power density concentration is so daunting. And from the requirement side, thanks to innovation, those standards, even those who have standards, the standards are always evolving. And the product requirements, because of this trend moving to more and more functionality, the product requirements are changing very rapidly, sometimes even faster than the silicon development cycle. And added to all that, the cost of designing an SoC is going up rapidly, compounded by the time, the verification cost of the complex design, the mask cost, and just the designing to the low complexity to take care of all these small geometry and adding the analog cost. So all in all, the opportunities there is no doubt. You see the big trend, you see the whole function, but to capitalize on that trend is not easy. So the traditional development methodology about a systematic, maybe progressive flow is under threat. It takes longer to fabricate a chip because of those advancements. It's more mass steps and also more other processing steps. It just takes long. You just have to take the time. And of those smaller geometries, higher, more complex design, more integration, it takes longer for timing closure as a designer. And for the complex chips, it also takes longer for verification, even you use IP. And we mentioned earlier on the requirements, there's always a rapid changes of the standard, the spec, and also the change of the requirements. Recently, like I was told, the PCI Express Generation 3, that spec, 830 pages, and they all have to be correct. So the specs are changing rapidly, and you have to design it, you have to make it work, and it's not easy. And everything adds to stretching the flow, the time, whereas the time to market has not changed. Your Christmas is still comes every December. So take the example of the Kindle. The first generation, I think the tagline is put your library in your pocket. And the most recent model, the tagline is put your life in your hand. But the important thing is you look at the architectural changes from generation to generation. It takes more performance, it takes more ARM core, it takes a lot more storage, it has new features, new functions, new standards, new interfaces. With this rapid architectural changes, the whole concept that it's just the IP reuse is getting to be not usable. You cannot reuse the same IP because the standards are changing, the functions are changing. And then talking about IP core. So as the transistor budget go up, as we talked earlier, we try to use IP cores to mitigate the risk. So you cannot design everything from scratch. You get IP cores to integrate it. The problem is if the IP core is not optimized for any application, you often result in integration complications. And also sometimes the architect has to compromise the feature set for to work around the IP. Because a lot of times it's the same. If it's an old standard, you just have to reduce your spec. You have to the interface may not work properly. So it is every single compromise will add risk to your schedule and your integration. And as the number of the IP blocks go up, the risk also go up, and that means the probability of on-time delivery go down. So talking about standards that forever evolving, this is the Ethernet standard, the IEEE 803, which is a very boring standard. But it has gone through 45 changes in the last 3 decades. So with this change, the IP reuse model pretty much get undercut. You cannot rely on building the IP once and use it again and again. With the rapid change of technology, process, with the rapid change of product requirements and standards, the IP reuse model is very difficult. And you have to make sure it works. You have to make it to design the change. So the whole IP reuse concept that has been kind of advertised, talked about several years, is under siege due to the rapid changes in standards, changes in technology, changes in requirements. So the reuse is, again, challenging to start with. Basically, it's just not enough. But on the other hand, IP is still the solution to solve this design complexity issue. You still have to integrate it because you just cannot imagine with today's transistor budget design everything from scratch. You have to think about how to make that work. So on top of that, let's talk about some of the SoC design. The SoC operation really depends on the cooperation of the hardware and software. The whole concept of SoC is a processor to run software and you have other hardware pieces to run it. So they are supposed to, the hardware are supposed to work together in this case, but every SoC design has to run into this what we call the hardware-software conundrum. Yes, they work together, but they have different objectives. Okay, to illustrate my point, let's look at the mind of a hardware engineer. in the hardware engineer, they always concept about the platform being very well structured with defined elements of processor, memory, peripheral, and storage, and very well defined interfaces. More important, their concept is when it's built, it's done. They're not going to change it, or very little to change it. And let's look at the mind of a software engineer. It's a maze of information. Every module, every layer is connecting to everything else. And in their mind, it's always changeable. It's just a matter of when. And in reality, the end product needs the operation of the two together and deliver. So in the SoC design, the hardware-software partition, how you decide which tasks run on software, which tasks run on hardware, is usually a big decision. It has to be a big decision for every SoC architecture. Using the hardware to design the functionality gives you what we call the PPA advantage. P, performance, P, power, A, area. It's always the most efficient. Using the software to deliver the functionality gives you the flexibility because you can change it in the last minute and also give you the overall time to market advantage. So I think at the end of the day, the SoC architect should have the freedom to take the hardware-software partition, which is most optimal for the design. They should be the ones to make the call about what's the right balance of the hardware PPA advantage versus the software flexibility and market timeliness. The hardware architect should not need to compromise their product spec or the design because of the rigidity of the IP, which is a lot of the current IP model work because if they have to look at, oh, this is all I have to work around it. They should not need to do that. Our vision is when you move forward, the IP should be customizable for the SoC requirement rather than the other way around. So practically what our thinking in Cadence, including like now me consolidating it, is the whole way of doing IP business does not work. One of the older days is what we call the IP bazaar, which main concern is about availability and price. You go from place to place to look at which IP may be useful for your design, and you bargain for it. For the lately, there's some IP mall or IP superstore that you can buy a lot of off-the-shelf IP from a superstore in one place, but you still have to decide which IP best needs for your architecture. And oftentimes you may have to change the product spec because that's what you can get. So in Cadence, we think the IP model moving forward is what we call the IP factory. You can build the IC which is customizable to the SoC requirement. So let's take a look at what exactly about this application optimized IP. So a mobile application has a set of requirements. You have to meet the constraints of power and compute. And for a consumer application, even though you want similar kind of interfaces and power, but it does have a different requirement. It can be more tolerant on power, but it needs a much more higher bandwidth for some of the interface. And similarly, for a cloud application has yet another set of requirements. Right? So each one of it you should have tailored for that. And I say that within the mobile application depends on whether you're doing your phone or your GPS. It's also different. This is just a very hypothetical representation. So on the IP offering, we need to have a very comprehensive offering of a wide range of IP to fit this wide range of applications, not just a tailored one and then you pick one. In the old days, you get the RTL and you go and model. We have to look at it that way. It is more so now than ever. SoC is a collection of standard IP but not just disconnected. They need to be integrated together, they need to be optimized, and they need to be optimized for the end application. They cannot be just standalone. IP cannot be looked into as a standalone IP anymore. You need to look at the fact that they're easy for integration, they're optimized, and they're verified. So you actually verify in the sense that like you build the subsystem, you make sure the IP work together, and it's designed to be correct. So Cadence right now offer a wide range of the interface and analog IP, which is like a wide range of the market. And for the verification, having a range of the verification IP is also playing an important role. And in Cadence, there's a large range of like VIP, which has like support all the protocols, simulators, languages. So it's getting to be like very extensive. So moving on is the hardware-software partition problem, as I mentioned earlier. So we have the hardware, which gives you the PPA advantage, and we have the software, which is more flexible and give you the time to market advantage. In other words, the software solution gives you more flexibility and functional diversity, but a lot of the time, the high compute and high bandwidth application or function cannot be done in software. You cannot just every time go out to memory fetch it and take all these steps because they are very parallel kind of like computation. So those hardware blocks, those functions need to be are often implemented in hardware logic. So that's how the architect needs to think through about that partition. But once the hardware logic, even though it can provide the efficiency and the performance, it is takes a long time to verify, and once it's even as verified, once it's tape out, it's very rigid. You cannot change it after tape out. So in Cadence and from Tensilica, what we have is what we call the data plane DPU IP. The DPU combines the software flexibility with the hardware logic efficiency. It can perform or produce for some specialized function, it gives 10 to 100 times better performance than the general DSP and CPU. So the data plane, the DPU, the target functions are those with high compute and high bandwidth, like the baseband physical or map layer computation, the voice, audio, sometimes the image processing, video processing. Those are the high data intensive applications. So with the software programmability, the DPU can maintain multiple standards because like it's a software programmable. So in some cases, the architect can decide to have like two markets but on one chip, just different firmware, and that could lower the development cost. Or some cases, they can upgrade to like extend the life project by firmware upgrade, or adjust to the changing standard, or changing or even add functionality without a silicon restring. So with the DPU offering, we believe that we can give the customer much more the ability to build more differentiated and competitive products. And every DPU coming out from Cadence Tensilica is generated on the fly, or basically generated according to spec with what we call the processor generator. We take the processor configuration description, and in a matter of minutes, sometimes hours, we generate the RTL for that processor specification and simultaneously generate the software tool for the same processor configuration. And the generated RTL can be taken to like target for any silicon project with standard cell library. So the product architect will be able to generate a DPU from a processor generator, target for a wide range of applications, like in the mobile area, it's imaging, audio, in some case baseband, and other market also in the SSD, the storage, camera, printers, some network equipment. It's all over the map. So our belief is like, again, the IP needs to be generated, needs to be customizable to the SoC specification. The next generation IP needs to be built with quality focus, needs to be like easy to integrate. It's also requirement driven, like what the other architect wants. We build what they require, no more and no less. And the SoC needs to be customizable for the end and the end target, and no compromise here. So there was Cadence. I'm new to Cadence, but I'm going through this year. Cadence has gone through a few acquisitions. Cadence itself has always been has a long history of doing the DDR and the PCI Express and other interface IP. And through the Cosmic acquisition, it comes with a range, a very complete set of mixed signal and analog IP. And Cosmic joined Cadence in May. And through Tensilica, we joined Cadence in April. With the extensor generator, they can generate the GPU for data plane processing. And through the Electronics, which joined Cadence just last month in June, with the Electronics controller, Cadence now has a complete set of interface IP solutions. So in summary or in conclusion, I want to say that we are building the IP factory. We, as newcomer to Cadence, and what Cadence has been there in the IP, pushing the IP business. The IP itself has to be correct by design. It's optimally configured. It's also software optimized. Ease of integration, and also changeable, meaning it can be targeted and customizable for the SoC requirements. That would help to drive the industry to build better SoC. Thank you.
We have 10 minutes for questions.
Once you ask a question, please raise your hand. I'll give you the mic. And please state your name first.
Michael, the question here is, what makes Cadence really stand out? Because being an IP factory, many other places could also serve that purpose. For example, Intel, for example, Marvell, for example. All these are kind of capable of being a IP factory per se. On the other hand, is what does Cadence really have that the other houses would not have?
So I would say that IP business is evolving. It's actually since I come from Intel, going to the IP business, I know how different it is from a semiconductor company to an IP company. ARM started, I think, in the early 90s, and at that time, in the early days, the IP is not very popular, and it has took time to mature. And in fact, today, if you look into the mentality of a semiconductor company, they build a chip. It's very different to say you build a design that's integratable and usable by others. So I'm not aware of Intel selling IP in any big way. And Cadence, as a tools company, has been supporting a number of design teams for a long time. And definitely, they also view that to jumpstart this company. That's why they're also doing all this acquisition. I think that all in all, IP is still a very young business within semiconductor. It's a niche market in the 90s. Has come to really coming up in the year 2000. It's going through phases. And Cadence and the newcomer like us are trying to make it work. And we also, as talking about Tensilica, we have 15 years of IP experience. We ship 2 billion cores. We have more than 200 customers, including 8 of the top 12 semiconductor companies. So we do bring some experience in that, and part of the acquisition is Cadence want to bring this experience and work with their team to make that happen.
want to have a question. So first, I really want to appreciate this is a very good presentation. The first time I learned other than CPU and GPU and there's a DPU. It's the industry changing, and so we welcome the new concept. And I want to toss a little bit further because I saw the Cadence has, acquired a lot of companies and also developed its own IP on the cores and also around all this interconnection surrounding areas. And I just wonder whether the Cadence can consider someday in Ghana to provide a tour for the SoC solution, just become an SoC company, to win the business against Apple or Qualcomm. What do you think about that?
Well, I mean, I'm definitely too new to Cadence to make that remark, but that's just, I think at this stage, if you look at it, being an IP company is actually very exciting. And in some ways, being an SoC company is good, but it's less exciting. and in some way, it's like you look at the supply chain, like where is the semiconductor come from, where is the transistor come from, and how it's building up. It's really the foundation that need to build up to the SoC. And overall, I think Cadence will still stay around the tools, the supply, the foundation area, which is where its strength, where the company is built from. And from my perspective, IP is an exciting space, and I don't think Cadence would go into, in my opinion, Cadence is not going to SoC company anytime soon.
This is wonderful because when I first started my career about 15 years ago in Silicon Valley, and people tell me that when you come to work for a hardware company, you either design IC or design IP. And for most of the people who work successful, they're doing IC, and the IP companies barely survive. Now we've seen a completely different story. IP seems to be more exciting. Thank you very much.
That's my personal perspective. So.
Yeah, my name is Ralph Chen from CASPA. I do have a question about your DPU. It sounds great. I mean, you have the flexibility at the same time try to achieve the PPA. However, based on what I heard from your description, it is kind of software driven to get the result, because in order to get the flexibility, that's the way to go. However, my question is, ideally, that's what we want, right? However, if your engine, that means your engine has to have a lot of expertise in that area in order to generate a very efficient, flexible, like what you said, the PPA, to achieve the PPA. And then, isn't it true though, the industry actually goes the other way around? Look at Apple. They basically handcraft and eliminate a lot of the bell and whistles, because we are in an area we have to make device which runs at very low power.
Yeah.
So my question is, how can Cadence or Tensilica achieve that, even though that's the goal?
Okay, so let me give you one example. One of the flagship product or application that we have is actually in the audio area. Our audio solution has gone to many different applications. Now, you can look into, of course, like if you do an MP3 hardwire, you could be much more efficient in like just do the MP3 or in RTL logic. Our audio code probably runs around, I would say, 300K or gate. But the difference is it runs 90 codecs, not just MP3, but DTS, HD, Dolby Volume, and there are new standards coming out, new codecs coming out, and they don't need to change hardware, you just port the software. And if you counted the number of hardware blocks in order to run 90 codecs, each one of them is different. The power is actually much more expensive. And on top of that, we also have this like big little concept that we have like the same software can run on a small core and voice trigger is actually like listening. Like you call the machine, say, wake up, and you wake up. But you have to be listening all the time. You cannot have your big processor or your big and those algorithms can just port on it and run in the software form and add it to the functionality in no time. So if there's a balance there, yes, if you truly want the efficiency, the functions that I also have to say some of, like for example, a lot of the HD decoding, H.264, when there's not a whole bunch of video codecs out there, doing the video in hardwire, that's the way to go because it's more efficient. You do it in software, it's hard. It burns a lot of power, and there's not enough codec out there to say you're doing a programmable solution. But on some other cases, you actually much rather to have that my same codec could run, my same processor can do the noise cancellation, can do all sorts of voice processing, can do like one time I can do the MP3 playing, and the other time with AAC is on the same thing, and then it becomes more powerful in the sense of like there's not the power burning powerful, but it's a powerful statement to adopt that.
Okay, Michael. Oh, after me?
No, just you.
Oh, it's okay, thank you. Michael here again. The question here is, here we have a room full of Chinese professionals, and some of the veterans from Silicon Valley already repatriated to China, and either educating or trying to establish a human wave workforce there. I mean, they are capable of punching out IPs with software and hardware. So there must be something that Tensilica or Cadence so far have been doing that would differentiate the massive force of creating and implementing hardware or IPs on the other side of the Pacific Ocean, right? Because otherwise, I mean...
I believe that I don't know that I believe that Cadence actually has a very big workforce in China. But I don't know the details of it. Like in Tensilica, we do have a small development team in China. Actually, in Tensilica, the development team wasn't very large, but there's a small one in China. And we do have a good market in China also. Even a lot of the Chinese companies doing the SoC have been our licensee. So we do reach out in there, and we have been found a viable solution for many of the applications, and we're happy to do that. And we also have a pretty good penetration in both Taiwan and Japan, and Korea too. All right.
An introduction on the IP factory concept, and it's our Dr. Liang to present our creation of the factory. That concludes our keynote session. We will have 10 minutes break. After that, we come back for a more exciting discussion on make versus buy.